Okay, I'm going to work through a problem for you guys with the truss analysis. So I'm going to look at the truss that I gave you in class. See if I can draw this. I'm not positive I had this correct. I'll draw it as well as I can, and the same method would be applied. I think this was 3,000 pounds up here, 3,000 pounds on this one, and we end up with 20,000 pounds right here. So the first thing we might want to do is we might want to label these, and I'm just going to label these as these nodes as A, B, C, D, and E. And we also want to give the dimensions. So the dimension here is 15 feet, and another 15 feet over here, and another 15 feet up here. So we have a nice symmetric truss. That'll be 20 feet right there. And the other thing that you guys should realize is that one of the reasons I chose these is if I were to then divide out this triangle right here, the dimensions of that triangle would give us such that we could then have, let's see, 7.5. This would be 20 feet. And this right here would be our hypotenuse, which would just be the square root of 7.5 squared plus 20 squared. And let's see here. Now, the first step that we want to take is actually we want to find out what the reactions are. So we want to find the reaction at D and the reaction at A. And I'm going to go about this the long way, although you might know exactly how to go about this right now, recognizing that it's a symmetric truss. And so let's actually use the recognition that it's a symmetric truss to check our work right now. So I'm going to take the sum of the moments about A. That is, if I were to take all the forces about this one point here. So that is going to be equal to 0. So I have 3,000, instead of writing 3,000 pounds, I'm going to write 3,000 kips, little k, superscript k, multiplied by this distance right here, which is 7.5 feet. And this is still rotating in this direction, so I'm going to say that this is the positive direction. So I have plus 20 kips multiplied by 15 feet, and then I have 3,000 kips, still in the same direction, multiplied by, now I have 15 plus 7.5. Minus my RD, it's minus because it's going in the other direction, and the distance to it is 30 feet, is equal to 0. And now if I solve for RD, which I happen to do for this already, ends up being that RD is going to be equal to 13 kips. So what's the other way that I could do this? Well, let's see, I have 3,000 plus 20,000, 23,000, 26,000 down symmetrically loaded. So therefore half of the load will go here and half the load will go there. Well, half of 26,000 or 26 kips is 13, so this checks. So I could also say, therefore, RA is also equal to 13 kips. So my next step will be to do a method of joints about, let's pick on A. So here we go. We have method of joints at A. So I'm going to pull out all of my forces, external forces on A, and then look at what the forces are on the truss members themselves. So this is what it will look like. Here's my member A. have my reaction force that's coming up, which I now have calculated to be, well, I'll call it RA at this point, but I know what that is. That's 13 kips. And then I also have my other forces. So somehow I have a force that's in this direction and this direction. I'll call this F, internal force. I called it R in class, but I'll call it F here. FAB and FAE. That's more consistent with what your textbook has. And so now I want to figure out what direction those forces are, and I also want to pick maybe some axes. And because they're all going to sum, all the forces are going to sum to 0, I can really pick any axes that I want, but I'm just going to pick the standard horizontal and vertical axes. So I will need to break my FAB up into FABY and FABX. So I'm not sure what direction it is, but look, I have an upward force. This FAE doesn't contribute anything to the upward force, so FAB has to have a downward component to its force internal. So then I end up with FABY down, therefore FAB is in this direction, and FABX is in this direction. That makes FAE in this direction, to the right. Okay? So now what I would do here is I would just sum my forces in the y direction is equal to 0. And I can say right here from my free body diagram that FABY is equal to RA. And I know that my RA is equal to 13 kips, so therefore my FABY is equal to 13 kips. And then I would sum my forces in the x direction is equal to 0, and I end up with FABX is equal to FAE. Well, we have this relationship between our horizontal and our vertical of 7.5 and 20. So let's use that, because what we're really doing is we're talking about a ratio when we're talking about any of these angles, whether it be theta or alpha or whatever we might want to define them. And we have a right angle here. So let's see. How are we going to relate FABY to FABX? So I'm going to say that FABX is 7.5 20ths of FABY. Right? That would make sense. So if I'm looking at this, it's going to be, this is a portion of this. How much is this? This is 7.5 20ths of this, which is 20 20ths. So we end up solving this, and we end up with FABY is then 7.5 over 20 multiplied by 13 kips. And I haven't done that out yet, but that's how you would find it. And you also recognize that FABY is equal to FAE. So I might go back to this. And so now I've found this one, and I have found this one. Okay? Well, hold on here. Have I really found FAB? FAB, if I have FABY, 13, and FABX, which is this right here, then my FAB will then just equal the square root of FABX squared plus FABY squared. Just using Pythagoras, I'll find the magnitude of it, and I recognize that it's pushing on the joint's pushing back, so therefore I have found this to be a compression member. And let's see, FAE, that's pulling on the joint, so it's equal and opposite pulling on the member, so that's a tension member. All right, so I have both these, and look at this. This is a symmetrically loaded truss, so I'll have this one and this one, so I can kind of check those off as I go around. So the ones that I don't have is I don't have this one, or this one yet. So let's pick on joint B and see how far we can get with this. So here's my joint B. Joint B, if you remember, that's the one that's up here in this corner. So I'll have an external force of 3,000 pounds, or 3 kips. And then I have my internal force, which I know what this internal force is. Right here, it's pushing, hold on, it's pushing on this member right here. And I also have a force that comes off this way. So this is my FAB. I also have an FBC and an FBE. Oh boy. So I have these two unknowns. I know this one, I know this one. I know that this one's going to break up into its two different components of FABY and FABX. But this one's also going to break up into two components, and I don't know what direction. And this one has a direction. So there's too many unknowns. I need to figure out some other way. So what I'm actually going to do is I'm going to do a method of sections, and I'm going to come back to this joint B. So I'll set this aside. I'll come and look at this again, my truss, and I want to take a cut. I want to take a cut in this, so let me redraw my truss over here and then think about how I want to take my cut. So that I can capture one of these. So these are my two unknowns. This is an unknown and this is an unknown. So I want to capture one of these unknowns by taking a cut and then taking a sum of moments about one point. So what I actually want to do, and this comes with experience, is I want to take my cut through here, and I want to sum my moments about this point here, which I have defined earlier as point E. So now let me just draw that. I'm going to blow it up a little bit so we can see what the members look like. Looks like this. We end up with our A over here, which is 13 kips. And we have a downward force right here of 3 kips, an external force. And now here's our point right here, E. And so I'm going to sum my moments about E, and then I'm going to find I have a force in all of these members. So this I already know, FAE I found. This one I don't know, FBE, and this is the one that I'm actually going to find now, FBC. So how am I going to find that? Sum the moments about E. That's going to be equal to 0, so put my finger at E. So these two forces aren't going to contribute at all because they're in line. It's an axial load coming right down to this point. So that's just like taking this member and I try to rotate this by pushing on this member. That's not going to rotate it at all. I have to have a force that's perpendicular to that moment arm. And that's not the case here. They're in line with it. So these don't have any moment. Even if I were to try to sum them, I would have FAB times the moment arm of 0, so therefore it's 0, or FAE times the moment arm of 0, therefore it's 0. So here I have, let's see, I will make, I don't know, this positive. Why not? So I put my finger here. This wants to rotate it. Our A at 15 feet away. This is going the other way. Minus 3 kips, the external force. And that is a total of, let's see, drop this right down. That ends up being 7.5 feet. And now, I'm not sure which way this goes. Let's say it goes this way. That makes sense. Would it go that way? This is 3 times, yeah, it's probably going to end up going that way. So it's minus FBC. And now, since it's in this direction, the perpendicular distance between these two, right angle right there, no matter where it is, it could be located way over here, it could be located way over there, but so then we just pull it back to this spot and we end up recognizing that that is 20 feet, that's equal to 0. So I plug in right here, I plug in my 13 kips. Did I actually do this? Did I sum this? Yeah, so when you solve for FBC, don't ask me why I solve for some of these and not for others, but FBC, I ended up with 8.625 kips. All right, and I found that to be in the same direction as this, so it is pushing on that member. So this is a compression member. So if I go back here, I see that this is a compression member, and I have in fact now found that member. So the only unknowns are these two. So I actually go back to this sketch right here, and I would break up my FBEY and my FBEX, and I'd say I just randomly pick that it's in this direction. I don't know if it's in that direction or not. Actually, I do know. But if I don't know, I'm just going to pick any direction, and if it ends up being that the forces summed, or when you solve for this, when you sum all the forces and solve for this one, if it ends up being negative, you have guessed wrong. So in this case, I do sum of all the forces, and I might pick the x direction is equal to 0. And let me just write all these in. I would have FABX, and this F, so that's a known, minus FBC, and that's in the x direction, so I wouldn't have x or y because I didn't break that up, so that's a known. And I'd have a minus FBE. All right, and that's what I'm trying to solve for. So, and that's going to be in the x direction itself. So I pick on everything that's in the x direction. And if I wanted to pick on everything in the y direction, or I could use just, once I find this member and I know this angle, I can find what FBE is directly, right? Or I could look at the y direction, just so we have this kind of method already established here. So we could end up with, let's see, we end up with a negative 3 kips plus FABY, and the way that I have this oriented, plus BE y is equal to 0. All right, so there's a lot of bookkeeping and stuff like that, but now I have actually solved for all my members, and I should end up with those members coming out to be the same, whether I look at it going from this side or from this side, because it's a symmetric truss as far as the geometry, and it's also symmetrically loaded. Therefore, all the forces will be symmetric internal. Okay, that's it.